Okay, ladies, so this is section 3.1, and I just want to go over some homework problems with you all because I know I will not be able to do that, and I wanted to go over some homework problems because on Monday I actually want us to start working on the homework from section 3.2, which I'll post that video later. So let's just look at 3F. Okay, so this is 3F, and it's asking us to find the domain and range for the relation W or R given by X, W, Y if the absolute value of X is less than 2 and Y is equal to 3. So it may be helpful here to draw a picture so we can draw a quick graph of what's going on. Now remember, from the definition of absolute values, it's the distance from the origin, right? And so that's another way if you want to, in terms of defining what our absolute value would be. It's negative 2, X is between negative 2 and 2, and then Y is equal to 3. So Y is going to be this horizontal line here, and then X is between, let's call that negative 2, and this is 2, right? And so that means, and it's less than, strictly less than, not equal to. So that means we know that our X values will be on this interval, and the Y values will just always be, right? It's just that Y equals 3, that's your output, right? And so the domain and range is pretty straightforward, or should be. The domain of W, that's our notation we use, well, that's just going to equal negative 2 to 2. So the domain can be in set notation, but in this case it's an interval notation because we're talking about our real numbers. And then what about the range? So if you want, you can sort of pause the video and see if you could try it yourself. But you should know it's 3, right? The set containing 3. Okay, so we need to write that in set notation because it's just one distinct number. Okay, so the second problem is giving you this set R where the relation is x, y, where they both come from the real numbers and y equals 2x plus 1. And they want to know, does 4 belong to the range of R? Okay, so, well, let's see. It's a line, so automatically if you know that this is going to be true, because remember the range is your outputs, and the range for this line, if you think about it, is all reals. The domain is all reals. But in case you're not convinced, remember it's your y value that we're looking at. So we want to know, does 4 somewhere, is there x, does there exist an x that will give you an output of 4 in the reals? Because x, the domain comes from the reals. X values comes from the reals. So 3 equals 2x. And so divide that by 2. So x equals 3/2. And since that belongs to the reals, we can say yes. 4 is in the range. Now, no, if I asked you if, let's say, this went from the integer z, right? If it went from z to r, then this would be no, right? Because there doesn't exist an integer that will give you an output of 4. But since we're on the real numbers, the answer is yes. Okay, ladies. So the next example is number 7, E and H. So you're given these 3 relations, R, S, and T, where we have here. So you see that. And this is with composition. So I'm doing these examples because I want to make sure you understand what the definition says. So S composed with R. Remember with composition functions, this is pre-calc stuff that I actually just taught in pre-calc, but now it's in foundation. In terms of relations, remember that you start with the innermost function there. So we're going to start with the innermost relation, so R. So you just look at the first pair in R, okay, or element in R, I should say. And so 1 goes to 5, right? 1 relates 5, or 1 goes to 5. Well, 1 goes to 5, so then you look in S to see if there's a 5 in the X place, in the X coordinate place, and it's right there, right? So that means, let me write my set notation first because it is representing a set. So that means 1 will go with 5. So you start, whatever that number you start with here, you relate it to its pair. So 1 goes to 5, and then you look in the next relation that's given and look for 5 and see what that goes to. Okay. And then let's see. So one, and if it doesn't go anywhere or if it doesn't exist, then that means you can't put that element in there. Okay. Because it has to exist. So let's look at the second one. 2 goes to 2 and then 2 goes to 4. So that means 2 is going to 4. Okay. And then let's look at the next one. So see if you can get the next one. Let's see. 3 goes to 4, but there's no 4 in S. So we skip that one, right? That one's not in there. But then let's look at the last one. 5 goes to 2 and 2 goes to 4. So we have 5 going to 4. So in the composition S composed with R, there are only 3 elements: 1, 5, 2, 4, and 5, 4. Okay. Since this is a video, if you didn't understand that, you can go back over it. I would suggest pausing the video now and seeing if you can figure this one out on your own and then come back to the video. Okay, welcome back. Hopefully you just didn't keep playing the video, but you actually tried it. And so now let's see. Parentheses, order of operation. So we need to do this first and then we'll take care of that later. This is, okay, composed with T. All right, so let's look. So let's take care of our composed with S. So starting with S, we got 2 goes to 4, and then, so 2 goes to 4, and then 4 is not in R, so we can't go anywhere with that. And then we have 3 goes to 4, and 4 doesn't go anywhere with that. Then we got 3 goes to 1 and 1 goes to 5. I'm sorry. Hopefully my writing isn't blocking your understanding. And so we have 3 going to 5, 3, 5. And then the last one, 5 goes to 5 and then 5 goes to 2. So 5 goes to 2. All right. We compose that with T. All right, so let's see what we'll get as our final answer. So now we start with T because T is our innermost relation. And so T, 1 goes to 4, and then you look, remember, you're looking here now, right? So there's no 4 there, so we have nothing for T. And then what else? 3 goes to 5. Well, 5 goes to 2. And so we're going to have a 3 going to 2. All right, and then that's it, right? Oh, no, I'm sorry. Let's try. It actually will be it. I'm telling you the answer before we get done, but let's be consistent because it could turn out in another example that this is not the case. But now we have 4 going to 1, and there's no 1 in there. So this is actually our final answer. I hope that made sense. Okay, this is 9D, and I'm making this video before class on Friday, and so I'm pretty sure we won't get to digraphs because I think I'm leaving half the class time for you to do the quiz. So when you listen to this video, you probably have done the quiz. You will have done the quiz already. Hopefully you all did well. But digraphs is on page 156 and 157. It's really straightforward, so that's why I didn't take up class time to go over it. So just look over it, and here it's asking you to draw a digraph on the set, and you may actually get it from doing what we're going to do, although make sure you go back over that section because there are some things that you're going to have to take into account for the next section. Okay, but this is saying make a digraph on the set 1, 2, 3. All right, well, first 1, 2, 3 will represent our vertices, which what's going on? Okay, I'm sorry, this program isn't working. 1, 2, let's put it like that. 1, 2, 3. And so this is saying we have a relation. 1 goes to 3, and it's a directed graph. So 1 is going to 3, right? Because order matters, right? Because just because 1 goes to 3 doesn't mean 3 goes to 1. And in this case, it doesn't. And then 2 goes to 1. All right, so that's it. That's an example of the digraph. Okay, so this is the last example from the homework. I think this section 3.1, the homework shouldn't be too bad, but of course on Monday, although we're going to be focusing on 3.2's homework, if you have questions from 3.1's homework, you can also bring that to class as well. Okay, but this is a proof, and so we have to prove that the domain of S, composed with R is a subset of the domain of R. Okay. And I drew this sort of little diagram so we could see before we even get to the proof what's going on here. So R is going from A to B and S is going from B to C, right? And so if that's the case, then S composed with R, how would that look? Well, we know it's going to come, so let's say, of course, you don't need to write this down, and hopefully that yellow, I don't think that yellow shows too well on the screen, so let me try another color. So let's say you started with 1 and 1 goes to 2, so that means 1 is coming from A and 2 is coming from B, and then let's say 2 goes to 3. Okay, and since these B's are the same, we know if 2 is in this B, it has to be in that B, right? And 2 is going to 3. So what this is saying is that S composed with R, you look at R first, 1 goes to 2, and then you look at S, 2 is going to 3. So the domain of S composed with R is going to be in the, the domain with S composed with R here is going to be in the domain of R by itself, okay? And if I confused you, don't worry, we're about to prove it. And I know actually the proof sometimes, it's rare, but in this case, I think the proof is going to make more sense because I feel like I might have confused you guys right there, but I don't know. All right, so here we go. Let X belong to the domain, just like in all our proofs involving subset. Assume an element is in the first and show it's in the second, right? Well, okay, so let X be in the domain of S composed with R. All right, so what that means is there's going to exist let's call it a Z that belongs to C, such that XZ is going to belong to S composed with R, right? And you can go back and look at the previous example when we actually have to find it when we were given definite numbers in the set. But we know that to be true, okay? Thus, there exists a Y in B, right? Such that XY is in the relation R, right? Because you have to start somewhere. X goes to Y, and then and Y is going to go to Z in this case, right? So X goes to XY is in R, and YZ is in S. Okay. Well, thus, since XY is in R, then X belongs to R, right? By the definition of relation. So therefore, the domain of S:R is a subset of R. And we are done with this video. Make sure you look at the next one as well for section 3.2.